Welcome back. We're now going to jump a chapter, actually 2 chapters. We're going to jump up to Chapter 8. And the reason why we do this is that Chapter 8 is on simple machines and the law of work. And we just got done with a chapter talking about work and energy, so it seems like a nice tie-in to go from that rather than going to momentum and other stuff to begin with that we'll cover later on. But in Chapter 8, we're going to look at simple machines. And again, you should remember this from 8th grade physical science. The simple machines, there are 6 simple machines, and we'll talk about these in a second. And we're going to talk about how to reduce friction and why friction is kind of the enemy in these machines. Okay? And we're going to start off with what's going to seem like kind of like a weird thing to say, but machines are actually tools that do not help us do work. And you're thinking, well, that's odd, because, you know, machines, I think, would make life easier. What they do instead is that they change the input force. Okay? In reality, a real machine will actually cause you to do more work by using it than if you wouldn't use it at all. But what it allows us to do is to change the input force. So it allows us to lift something that would be extremely heavy, what we couldn't necessarily pick up on our own, but we're able to lift that up. The trade-off is that we're going to have to move at a much greater distance than what we would have had to before. We're going to take a look at this. There are 6 simple machines, as you remember from 8th grade physical science, okay? And the basic ones that we're going to talk about, we're going to talk about the lever and fulcrum, okay? The seesaw, the teeter-totter, whatever you want to talk about it. The inclined plane, which we've talked about before in a little bit of detail, okay? And the other one we're going to take a look at, too, is the pulley. And actually, in our lab, we will be working on these as well. The other ones, we're not really going to investigate all that much. There are some different pictures on these. We can take a look at how they give us mechanical advantage and how they will change our input force. But we're going to focus on those 3, the lever, fulcrum, inclined plane, and the pulley. Now, as I've always said before, we've always started with the simplest case and then work to the more complex. The machine is actually, our simple machines are actually kind of bad because there's always some friction. And this is what causes us to say that a machine does not actually help us do work. We're doing to do work on the machine. The machine is going to do work on the object we want it to. But along the way, some of that work, some of that energy that we put into the machine gets lost, those quotation marks, to friction. And so we're going to start off by dealing with the ideal machines first, and the fact that we're going to ignore friction. We're going to assume, hey, there is no friction in this, and that way, in this case, the machine, whatever work we put in would be exactly equal to the work we get out. So, you know, an ideal machine, so ideal, that means there's no friction. We're going to ignore it. Okay? Now, again, you can see the note on here. These things do not exist in the real world. But it goes back to we'll always start with the simplest case and work to the more complex. Now, the law of work states, okay, and this is basically just a rewrite of the law of conservation of energy, of loco E. Okay, remember that work is energy, the energy is the ability to do work. And so our law of work for ideal machines states that the work that we put in, so W sub in, is equal to the work that comes out of the machine, or W sub out. So you hear me say this, win is equal to wout. And so if we were to look at this in terms of a diagram, and we'll do the inclined plane, if this is our inclined plane, this is the object. Now, obviously, we're going to have a force due to gravity pulling down on that. That's the force that we're going to have to overcome in order to lift it. So our force out, the force the machine exerts on the object is our force that comes out of the machine. That's going to equal our force due to gravity. Our force in, which I'll put in red, is we're going to push that along this way. And I'm not drawing these arrows to scale, so please keep that in mind. When we come in tomorrow in class tomorrow, we'll draw these a little bit more to scale. Okay? But remember our formula for work states that the work is equal to force times the displacement. And so I can write that over here. And you notice I've left some spaces there because we have a couple different forces. We have a couple different displacements. Our work in, that's going to be found by taking our force that we exert in. So how much are we pushing with this? In this case, with the inclined plane, how much are we pushing it? And then the distance that we have to push that force. And I'm going to put that in an orange. Actually, I don't want orange. Let me change that color. That goes better with our force out. Put it in a blue. We're going to push it this distance. So this is our distance in. Now our force out, I'll put that back here, force out, that's overcoming gravity. And so our distance out, that's going to be how far the object gets lifted. And so I'll put that in orange. This is our distance out. Now remember our rule for work, and that the work done, work stated, work is equal to the force that is parallel to the displacement. So if you look at the force that I exert in, it's parallel to the length of that plane. And so my distance in has to be parallel to that. My force out, that's going up, that has to be parallel to the height that I'm raising it up. And so that's how you can always link these together. So if you're not sure which distance goes with which force, you look at which distance is parallel to which force, and you combine those two. So you hear me say this, so win is equal to out, or finned in is equal to fout out. Okay? And again, this is an ideal machine, so there's no friction in this case. Okay? So we can actually rewrite these to see that there's a trade-off. And so if I take my finned in, and that's equal to my fout out, if I rewrite this, I can see that fin over fout, the ratio of the force that I put in compared to the force that I get out, that's going to equal the inverse relationship between the distances moved. And so if I want to make my fin be small, I'm going to have to make my din be big, because there has to be that trade-off. And so if I go back and look at my diagram, the distance out is less than my distance in. And so what that means is then that allows to my force in to be less than my force out. Now, we'll come back and we'll try these tomorrow. We'll try a couple sample problems with these tomorrow. But again, we'll deal with friction the next day. So everybody have a great night. We'll talk to you later. Bye.